All right, our task in this video and the one after it is to develop a valence bond description of the bonding in beryllium dihydride. Simple enough. This actually is the full Lewis structure for this molecule. It only has 4 valence electrons. There's no formal charge on this structure. There's an underfilled octet on the beryllium, but beryllium just doesn't have a whole lot of valence electrons, neither does hydrogen for that matter. So sometimes, or a lot of times, beryllium compounds, boron compounds as well for that matter, often have underfilled octets, but that's okay for now. So here are the ground rules. Each bond has to involve the overlap of the space occupied by one of the valence electrons on hydrogen and one of the valence electrons on beryllium. The alignment of those bonds, or now the overlap of the space occupied by those various electrons, has to be consistent with the known structure of beryllium dihydride. And what is that? Well, the beryllium hydride bonds, just like Vesper says, are known to be exactly 180 degrees away from each other. This is a linear molecule. And that both of them are identical. And the implication of that is that both bonds result from exactly the same type of overlap. Namely, they are the same types of electrons that are involved in that overlap. So the valence electrons we have available to us. On the hydrogen, it's pretty simple. There's really only one choice. It's a 1s type electron. The valence electrons on beryllium, we've got 2 choices. There are 2 2s electrons, so there are 2s electrons, and there are also 2 p electrons. Or let me rephrase that. Those are the states that are available to us. In the ground state, beryllium only has 2s type electrons, but you could give it a little. You could give one of those electrons a little bit of energy and promote it to one of the 3 2p states that are, not that far above. All right, so let's try to put this together. All right, ignore the white box. So the first scheme, let's try overlapping a 1s electron from the hydrogen with the 2p electrons from beryllium. Now remember that p electrons or p states come in sets of 3 that happen to be oriented 90 degrees away from each other. All right, and now I'm color coding the electrons here. Namely that this is where the wave function of that electron has one sign, and here it's got another. And so this is one of the 2p states. So this is the space that's occupied by one of those 2p electrons. And this is the space that would be occupied by one of the other 2p states. And remember that they've got that figure 8 shape to them, and those states are also physically oriented 90 degrees apart, or 90 degrees from each other. So, and I can call them, if we have to specifically call them something for p states, we normally just call them x, y, or z. So I just happen to label them px and pz. And the rule is that once you overlap an electron or one of these states with one of the other atoms, it's done. All right, so we could put one of the 1s states, let's say, overlapping it with a 2pz. And now you might want to say, well, can't we just put the other one right here? But no, once there's one overlap with a particular electron type, it's done. So we can't use, so the pz is spoken for. So the px state would be the one that we have to use. And so you do something like this. Now, this tells you that now both of these BEH bonds are going to be identical because they're both hydrogen 1s, beryllium 2p overlap. So they'll be the same length, they'll be the same strength. But they will be 90 degrees away from each other because that's the relative orientation of those p-type electrons. And that is incorrect. So this is not the way to put beryllium dihydride together because that structure is not what nature says it is. But all is not lost because along with these p states on beryllium, there was a 2s state available as well. So let's try that. So what would that look like? So we've got, for reference here, I'm putting on the 2pz. The 2s, remember, s-type electrons occupy a spherical region of space. They are roughly the same size. I think I might have just drawn the p state here, just a little larger for clarification here. So I could still make one of the bonds overlap between a hydrogen 1s electron and a 2p electron in beryllium, specifically an electron in the 2pz state. The other one I could put pretty much anywhere. I could put it there, I could put it there, I could put it there. So this would be hydrogen 1s, beryllium 2s overlap. The problem is that because of the spherical symmetry of that 2s state, or electron in that 2s state, that particular atom could be anywhere, which would give the hydrogen, beryllium, hydrogen bond angle, it would be undefined. It pretty much could be anything. So, and on top of that, the bonds are not identical because both of them, each one of them, I should say, results from different overlap. 1s, 2pz, and then 1s, 2s overlap here. So we have no idea what the geometry is going to be, and the bonds aren't the same. So we're still not right. But those were our only choices. Or were they? All right, think about this. We talked a little bit, not a little bit, but we did more than a little bit. We talked about the various types of electrons, s, p, or d, and the shape that they took. And also, we looked at pictures and talked about the relative orientations that the, 3p p states that are always together, their relative spatial orientation. I also showed you kind of what the d electrons look like and also what f electron states look like. And, if you forgot, go back to that lecture, look at those pictures, look at those orientations, and try to make a trigonal bipyramid out of that. And I'll wait. I hope you'll hit pause because I'm not going to actually wait. But usually if we're in a face-to-face class, I let people struggle with this for a couple minutes and realize that, yeah, it's kind of difficult to do. And so it turns out that if you look at the shapes that various electron states have, almost none of them, it's almost impossible to put together any of these structures that Vesper tells us is the actual lowest energy geometry of a molecule. So what's the deal? Either our original pictures of electron shapes are wrong, or Vesper is wrong. It turns out that both of them seem to be right independently. So what's going on here? Well, we haven't quite told you everything about these. So we talked about these electron states and the shapes that they adopt. That shape is often called, you will see if you have any other chemistry instructor but me and a couple of others, they'll use the word orbital to describe that shape. What are they? This is something people still talk about. But deep down inside, they are the result of a lot of math. We were talked about wave functions at the very beginning when we started talking about electrons. And that the equations, these wave functions that give us these shapes, the figure 8, the 4-leaf clover, all the other ones, are the result of a lot of math. And specifically, they are merely approximate solutions to a pretty nasty second-order differential equation. So if someone asks you what is, if you're in some trivia contest that has gone horribly sideways, and someone asks you what is an electron orbital, you can just look at them with all the confidence in the world and say that it's an approximate solution to a second-order differential equation. And you will be right. And if they don't tell you you're right, give me a call. All right, here's what I didn't tell you. that one of the neat little things about the kinds of functions that are solutions to that really nasty second order differential equation is that, so we can't use any function. And it turns out that one of the rules that ends up after looking at all this math is that there's a rule that says that if you have solutions, a bunch of functions that are valid solutions, that combinations of those functions are also going to be solutions. And when I say combination, I mean that strictly in, a very simple mathematics sense. So remember we talked about these wave functions where we call them psi, so the little pitchfork thing. And it could be literally something like the wave function that describes atomic state number 1, and the wave function that describes atomic state number 2. If you multiply them both by the square root of 1/2 and add them together, you have a new function. And it turns out that you can be rest assured that if these functions are valid solutions, this one is too. And here H is going to refer to what's called a hybrid state. So this is an atomic state. This is the wave function for a different atomic state. And this is a new hybrid state because it is a combination of those two. Mathematicians like to call this mixing, or this combination. They said these functions are actually the functions that describe these states are mixed to make new ones, these hybrid states. And so what we can do if we don't have a whole lot going else on, and at this point who does, we can actually mathematically combine the equation that describes the 2s state on beryllium with one of them that describes one of the 2p states on beryllium. I just randomly picked the z because by default, if there's one bond axis, or by convention, if there's a single bond axis, we just call it z. And I'm not going to show you that math because it's not pretty. But the result in one of the other rules about this combination is that whenever you mix states, you get the same number of states out as you put in. So if we're mixing two of these original atomic states, we get 2 hybrid states. And the hybrid states are usually labeled or named after the original atomic states that made them, or that was used in their creation. So in this case, if you're mixing an S state with the P state, we call that, for what I hope are fairly obvious reasons now, an SP hybrid. Right. Now, I'm not going to show you what the exact states are, but I will show you kind of what the picture is. All right, so, and you can actually do a lot. You can surmise the shape of these new hybrid states fairly well just with one simple rule. Actually, I guess it's 2. That it gets bigger where you're overlapping the same color, mathematically the same sign, and things shrink or get smaller when you're overlapping areas of opposite signs. So this is, we call this constructive interference here and destructive interference here. So, and I've defined the 2pz state as having the green sign on the left and the blue sign on the right. Now it's kind of an arbitrary choice. In the end, both of the results will be the same. So what's going to happen when we actually combine these functions is that we're going to get more electron density on this side and less here, and it's going to end up looking like that. Now, one thing that is new at this point is that the electron density around, so this blacked out here, by the way, would be the beryllium nucleus, and the electron density around there is not symmetric. There's more of it on the right side than there is on the left, which is not something we see in the original unhybridized atomic states. So the other combination ends up being, so this is, we'll call this sp hybrid number 1. The other combination is if we were adding them here, we're subtracting them here. And you may or may not recall that subtraction is simply the addition of the opposite. So what I've got here is I'm now going to subtract. So the rule is kind of reversed here. So technically, this I'm going to be subtracting blue from blue, which gives you nothing. And if I'm going to be subtracting green from blue, which is the same thing as adding blue to the blue. So again, imagine with this negative sign here, this is actually reversed. And in that case, what we get is actually the opposite picture. So we're adding the opposite. So in this case, on this side, we're overlapping blue and blue. And because of that negative sign here, we're overlapping green and blue. So we get increased electron density on the left side, and it's a little bit reduced on the right side. And this we would call sp hybrid state number 2. And these are also equal in energy. So just like the p states or all the d states, they might have different orientations, but in this case, these have the exact same shape. They're just oriented in a different way. Right. And now that we've got our hybrid orbitals, in the next video, we will actually put the molecule together. So stay tuned.